You know when you type something into an AI like GPT or Gemini and it just gets it? It's not magic, not really. It's all thanks to a groundbreaking piece of tech called the transformer. So today, we're going to pull back the curtain and see exactly how this thing actually works. And it all starts with one big question.
Right, this is it. This is the core of the whole puzzle. How does a machine go from just a bunch of letters on a screen to actually understanding context and nuance and meaning? Well, to get there, we first have to look at how AI used to do it, and, why it kind of sucked.
So, before 2017, the AI world looked totally different. The main tech for things like translation or predicting the next word in your text messages, that was all built on something called recurrent neural networks, or RNNs. But they had some pretty serious problems.
Okay, so these old models had two massive flaws. First, they had to read a sentence one word at a time, in order. You can imagine how slow that is, right? And it meant you couldn't use powerful modern computer chips to speed things up. But the second problem was even worse. They had terrible memories. I mean, by the time an RNN got to the end of a long paragraph, it had basically forgotten what was said at the beginning. It's this thing called the vanishing gradient problem, and it was a huge, huge bottleneck for progress.
So you can see the difference, right? We're going from this slow, forgetful system to one that can see everything all at once and understand the entire context. This wasn't just a small improvement, it was a total paradigm shift, and it was all sparked by one single breakthrough.
Yep, that moment came in 2017. A single research paper dropped that would completely change the future of AI forever.
It came from a team at Google, and the paper was called Attention is All You Need. And that wasn't just some catchy title, it was basically a declaration of war on the old way of doing things. They proposed this wild new architecture that is now, quite literally, the backbone of all the AI we use every single day.
These are the author's own words, and they're pretty powerful. Eschewing recurrence. I mean, that's just a fancy way of saying they threw out the old, slow, word-by-word rulebook, and they replaced it with this brilliant new idea called an attention mechanism, a way for the model to look at a whole sentence at once and figure out how all the words relate to each other, instantly.
So how does this thing actually read? Well, the very first step is to turn our language into the only thing a computer really understands, pure math.
And this happens in three main steps. Think of it like a recipe. First, tokenization. This is where you chop your sentence up into its basic ingredients, words, or sometimes even parts of words. Then, embedding. This turns each of those ingredients into a list of numbers, a vector. Finally, you've got positional encoding, which is like adding the instructions to the recipe, telling the model the exact order of the words.
The best way to think about an embedding is like a coordinate on a giant map of meaning. Words that mean similar things, like king and queen, or dog and puppy, end up really close to each other in this big mathematical space. This is how the AI starts to get a feel for the relationships between words. And this is exactly why that third step, positional encoding, is so absolutely vital. Look at these two sentences. They have the exact same words. Without positional encoding, an AI would think they mean the same thing, but they definitely don't, right? So this step adds a kind of numerical fingerprint to each word's vector that says, hey, this word was first, this one was second, and so on. It's critical for understanding grammar.
Okay, now we get to the real secret sauce, the core innovation of the whole thing, a mechanism called self-attention. This is where the magic happens.
All right, the easiest way to wrap your head around self-attention is to think of it like a really smart web search. For every single word it's looking at, the model creates three things: a query, a key, and a value. The query is like the word asking, hey everyone, who in this sentence is important to me? The keys are like all the other words raising their hands and saying, this is what I'm about. And the values are what those words actually mean.
So it all starts here, step one. For every single word, or token, the model generates these three separate vectors: a query, a key, and a value. These are learned during training, they're not random.
Next up, step 2. The model needs to figure out who's relevant to whom. So it takes the query from our main word and basically compares it to the key of every other word in the sentence. It's like a little compatibility check that produces a raw score for how well they match up.
Now, those raw scores are kind of messy, so in step 3, they get cleaned up. They're run through a function called softmax. You don't need to be a math whiz here. All you need to know is that this function turns all those scores into neat, clean percentages that all add up to 100%. This is the model literally deciding how much attention to give to every other word.
And for the final step,
The model takes those attention percentages, multiplies them by the value of each word, and adds it all together. And what do you get? A brand new representation for our original word, but this time it's packed full of context from the entire sentence. It's not just a word anymore, it's a word that understands its place in the world.
And check this out, here's what that actually looks like. In the sentence, the animal didn't cross the street because it was too tired. A single attention head has figured out that the word it is really talking about the animal and the fact that it was tired. It figured out the pronoun's meaning just by paying attention to the right words. Pretty cool, right?
But here's where it gets really brilliant. A transformer doesn't just do this once. It does it many, many times, all at the same time, using something called multi-head attention. It's like having a whole team of experts reading the sentence together. One expert might be focused on grammar, another on who's doing what to whom, and a third might be looking for the overall feeling of the sentence. This is how AI can start to understand really complex things, like sarcasm.
Okay, so we've been talking about words and language, but it turns out this incredible architecture isn't just for text. You can actually teach a transformer to see.
And the idea is just so elegant. You literally just chop up an image into a grid of little patches. Then, you treat each one of those patches as if it were a word in a sentence, and feed the whole thing into a transformer. The self-attention mechanism then goes to work, figuring out how all the different parts of the image relate to each other. It's a total game changer for things like finding objects in a picture.
So transformers are obviously super powerful, they're versatile, and they're the foundation of all modern AI. But like any technology, they're not perfect. They have their own set of challenges. So let's talk about what's next.
The single biggest issue is a scaling problem. Because every word has to pay attention to every other word, the amount of calculation needed just explodes as text gets longer. If you double the length of your text, you don't just double the work, you quadruple it. It gets out of hand fast. But clever researchers are already coming up with solutions like flash attention to make things more efficient. And we're seeing this tech expand into incredible new areas, like discovering new medicines and creating AI that understands text, images, and sound all at once.
The transformer completely changed what we thought was possible with artificial intelligence. It gave machines a whole new way of understanding our world. And that just leaves us with one final, very exciting question to think about. What comes next?